Okay, so this topics we separate into three different small days to talk about this. The first day we're going to talk about basic terminology related to this topic, about the fluid. And then the next one that we're going to discuss is about when the fluid start to in motion and what are the important property is going to change and how can we use that to do a calculation. So on Friday, you're going to hear a very important principle called the Bernoulli principle, and we will show you how you can use the Bernoulli principle. Then the last one, the last topic is going to be something about the viscosity of the fluid, which is very similar to the mechanics. When we talk about mechanics, we mainly focus on the interaction between the solid and solid. As you can see that when we jump into a fluid, it's even though they are different kind of state, but they share some kind of same property. So when you have a viscosity, meaning the fluid can also have some friction, and that's the viscous fluid that we will spend a little bit on this last topic. After the last topic, if we probably will have some time that we could go over some of the problem. All right, so let me start with this one here. So density. Okay, you probably already know density, and if you take chemistry, I bet you do the density calculation a lot. So the density, we know the definition for the density is very simple. The symbol that we use for the density is this one here. This is a rho, right? So this represents the density. And the simple equation to write the density is simply, you use the m divided by v. So what does the m represent? Mass, right? This is a mass, and v represents the volume. So that's how we define the density. And we know the density is related to, a lot of people know that density is related to whether an object will float or sink on a fluid, especially for water, that we use water a lot. And you know the density, if the density is higher than the density of the water, then when you put it on top of the water, it will sink. If it's less, then it will float. Why do we want to start with the density? Well, because if you want to describe a property of an object, it doesn't have to be a fluid. All things has a density, right? If I simply ask you a question, I have a block of wood and I also have another block of steel, then which one is heavier? And what will be your answer for that? Do you think wood is heavier or steel is heavier?
Steel.
I hear, I guess somebody wanted to say steel. This question is not actually a well-defined question. And the reason is this. If I have a piece of wood like this, but I have a steel just like this, then steel is not going to be heavier than the wood, right? So what I'm missing here is I didn't tell you the size of the object. If I didn't tell you the size of the object, you cannot simply say which one is heavier. Unless I say these two are the same size, then you certainly can be sure that steel is going to be a heavier object. And the reason is that actually that's the reason why we want to talk about the density, because the density is a better property to characterize or to distinguish two different materials. Each one of the material has a different density, and it's simply based on if you have the same size, how much of the of matter anyway. It is actually the atom inside of the material. So the atom that you have, if you have more, and then very likely you're going to have a heavier, you're going to have a higher density. One thing important about the density is the unit. So we know the unit for the mass is, it's not m, is actually kg. So the unit for this is kg divided by the volume, which is the meter cube. Okay. So you can also have a different unit for the density. Another unit that we use a lot is the gram per centimeter cube. You can also rewrite this unit for this one to be the gram per cc, right? So what does the cc represent? It represents the cubic of centimeter cube, all right? So centimeter cube is also equal to cc. And so that's the unit of the hint for the homework right after the class. I already recorded, so I haven't posted, but I'll post it right after this. I'm trying to get my notes. Okay. All right. So in order to find out the density, then you need two things. You need to know the mass, and normally the mass will be given, or sometimes problem will give you the weight. But you know what the weight is related to the mass, right? So if you are given with the weight, then you know this one is the mass times the g. So g is 9.8, and then you can convert it. The volume is another thing that you have to determine. So how do we find the volume? The volume for like a rectangular object, that's probably is very simple that you can calculate that. But if you are given with not like a rectangular object, such as like a sphere, as one of the most common one that you will see in the homework problem, if you have a sphere like a ball, then what is the equation for that? Well, if you have a sphere, then the equation for that volume is 4/3 pi r cube, okay? The r represent the radius. So 4/3 pi r cube, this is the one that you're gonna use the most. So make sure that you know how to find the volume for a sphere. So that's about the density. Now, another very similar property is called the specific gravity. Okay, I'm going to use the SG to represent that. So so what is a specific gravity? It's actually a ratio of the density between two objects. So if you have an object and you wanted to say what is the specific gravity of the object, you need a reference object. Well, the reference object that we use is water. So if you use the density of water as the reference and you use the density of the object, then the specific gravity of the object is going to be the ratio of the two density. Why do we use water density? Well, because we use a lot of things with the water to be the reference. One thing is the temperature and the other one is the density. So the nice thing about the water density is, by our definition, density of water is equal to 1 gram per cc or centimeter cube. So 1 gram per cc is the density of the water. This number 1 gram per cc is also equal to 1,000 kilogram per meter cube. Okay, so if you have a density of an object, you divide by 1, which will be specific gravity of the object. Okay, so that's another thing that we will use to represent the density. Let's do like one quick example over here. So a simple example to find out something of the related to the density. Okay, we have a sphere. Oh, let me erase this one. Okay, let's say I have like a sphere, like a ball of aluminum. Okay, so this is aluminum. And we're given this aluminum with mass. So the mass of the aluminum is 24 kilograms. And we want to find out, if I have this much amount, can you tell me what is the radius? What is the radius of this aluminum sphere? How can we calculate this? Well, you need one more information, which is sometimes you can look at a table in the textbook. I believe 11.1 is the table that gives you all this density. Well, it's not all, but some of the most common material density in that table. You can find that. So let me just give you the number. If we are given with the density of the aluminum equal to this, 2.70 times 10 to the third kg meter cube. Okay, so this is the density of the aluminum. Then how do we find the mass of this one here? So how do we start with this? Now you look at the equation that we have. The density is simply equal to the mass divided by the volume. And because of that, we are given with the density, we're given with the mass. Actually, what we need is the volume. So we can rewrite this as the volume is going to be equal to the mass divided by the density. And what is the volume equal to? The equation for the volume of a sphere, we just give you, that should be equal to 4/3 pi r cubed. So you given with this number 24, you given with this one 12.7 times 10 to the third, and you put this equation, then you should be able to find the r. So how did you do this calculation? Very simple and straightforward. You can verify the result. This r is going to be equal to 0.129 meter. Okay, that means the size of the aluminum, the radius is about almost like a 13 centimeter. And that's how big the aluminum is going to be to give you 24 kilograms. Okay, any question about this part? That should be very simple. All right, let me go back to here to look at the second topic I wanted to discuss with you, pressure. Okay, let me get some more space here. Talk about pressure. Okay. All right, pressure. Pressure is one of the important topic in this chapter. You're going to have several different calculations that you can do with the pressure. Now, first thing that we wanted to do is to define pressure. So P is the symbol that we normally use for the pressure. How do we define pressure? The pressure depends on the force. So if you like will use some of the object that you push something, then you're going to actually apply a pressure, right? So if someone push you, then you feel that force, that is actually the pressure force. So pressure depends on the force, and we know the larger of the force, the larger of the pressure. So it depends on the force. The other thing depends on the pressure is the area. So if you apply a force with a sharp object as opposed to you push to something with a dual area, then the pressure that you feel with the sharp acute object will give you a lot more pressure if you apply the same amount of force, right? So same amount of force, if you push to a smaller area, you're going to feel more pressure, and the larger area, you're going to have a smaller pressure. That means pressure in the area is inverse proportional. They are totally opposite. So in the equation, we're going to put the area at the bottom. So this is an area. So pressure is equal to force divided by the area. Now, not only are we going to define this, we also need to look at what is the unit of the pressure. Well, unit for the pressure, there are a lot of different kind of units. But the simple unit that we are going to describe just based on this equation is this. The unit for the force is Newton. The unit for the area is meter squared. So this is a unit for the pressure. But we kind of lazy. We don't want to say Newton per meter square. We define this one into another term, which is called Pascal. So if you see the PA, that simply represents the Pascal. Pascal meaning the Newton divided by meter square. Okay. Another unit system, which is the US unit system, they also have a similar one. And that similar one is so-called the PSI. You probably heard about the PSI a lot. So our water pressure is also in PSI. I don't remember the number, but the water pressure, I think, is about 20 something. So the PSI represents this. It represents pound force. So if you describe force in US system, we use the pounds. And pound, there's a pound mass, there's a pound force. So you should use the pound force. And the area will be described by inch square. So inch square per inch square, if you have a pound force divided by inch square, that is the PSI. Okay, PSI represents this. This is the one that we use the most in States. However, internationally, we use Pascal. Okay, so most of the calculation will based on the Pascal. You're going to use the Pascal for most of the calculation. And you can do a conversion. So in the textbook, you have a table of the conversion. You have to know how to do a conversion. If we give you the pound, if we give you the PSI, then you should know how to convert this into the Pascal. Now, in addition to that, and then we also have the unit for the pressure in terms of like a the mercury. Right? This is used the most when we do a blood pressure. When we measure the blood pressure, then we will have a number. That number is actually how much millimeter of mercury. That is one way that we actually measure the pressure. So it simply represents how much high of the mercury is going to be if you have that much of the pressure. And then we are going to do some of the calculation over this when we talk about the blood pressure. But you can also do the conversion for this one here as well. Another common unit that we use for the pressure is atmosphere pressure. So you probably hear about this one here. ATM. If you hear the ATM, that represents atmosphere pressure. So 1 atn, meaning a normal, like a common air pressure, that's the air pressure that you feel right now. Do you feel air pressure at all?
No.
No, you don't feel air pressure, right? Because air pressure actually exists around us. Where is the air pressure coming from? Well, since it's called air pressure, that means it's related to air. And you look at the equation over here, the pressure is equal to the force divided by area. So what is the force? What is the force coming from the air? Oh, it turns out it's this. So if this is an Earth, the air, the atmosphere is something that's surrounded with the Earth, right? So the air, we actually have layers of the air surround us, surround the Earth. And if you stand below the air, which you stand on top of the Earth, then all this air is going to push you, because each one of the air is going to have certain kind of amount of a mass. You probably don't see it, but there is a mass of the air. And they are attracted by the gravity, they are attracted by the Earth. And that's why the atmosphere is surrounding us. They are not going to escape. They're not going to get away because the gravity. They all attracted by the gravity. And because they're attracted by the gravity, they're going downwards. And therefore, all these particles is going to apply a force on top of you. And if you sum all these forces together, and that is the atmosphere force acting on you, and you divide by the area, and that is one atmosphere. Okay, so that is one atmosphere. For Earth, how we calculate this? We simply to find out what is this total area of the Earth. So Earth is like a ball that you know the radius of the Earth, that you can find out the total volume. Is actually the surface area of the sphere. I believe that is the 4 pi r squared, and that's the area, surface area of the ball. I'm not sure about this, but there's an equation that you can find out the surface area of the sphere. And then you calculate the total amount of the air surrounding us, and you divide and you multiply with the g, and then you can get the force on top of you. So that's one atmosphere. So my key point here is, if I have one atmosphere, and how much Pascal would that be? Well, it turns out if that's the unit for the atmosphere, then 10 to the 5th Pascal is equal to 1 atmosphere. So these two are equal. This is also equal to 14.7 psi. Okay, and this is also equal to 760 millimeter of mercury. So these are all equivalent. If you do the unit conversion, you have to use this one here to do all the conversion of calculation. The last thing I want to talk about the pressure is this. Pressure is equal to the force divided by the area. Do you think the pressure is a vector or scalar?
Scalar?
It is a scalar, right? That's kind of very strange, right? If that is equal to force divided by area, how come the force is a vector? How come this is not a vector? Well, it turns out when you use this one to do the calculation, this force is the force that is perpendicular to this area. So if if you put like a block, let's say this is a block, and you put this block inside a tank, and in the tank I put some water here, so this block is going to feel some kind of pressure, right? So if you are the person inside of the water, and what you feel, the top of you going to feel the pressure, and where is the pressure coming from? Well, the pressure is going to coming from the top of you. But if you are on the side, your side can also feel the pressure. So on your right hand side, you're going to feel the pressure coming from the right hand side. And left hand side, you're going to feel pressure from the left hand side. The bottom of you also going to feel the pressure from the bottom of you. So each side, and it doesn't matter where where you are, the pressure force is always perpendicular to you. So this is actually the pressure that you feel, and it was because the pressure. Why do we say pressure is not a vector? Because pressure doesn't have a specific direction. It has the force which is perpendicular to the surface area, but it doesn't have a specific direction. I cannot say the pressure go to the right, go to the left, because it's everywhere. It's all directions. So it's actually a scatter. But pressure force, if you talk about pressure force, then pressure force has a direction because force is a vector. Okay, so the force is always perpendicular to the contact area. Okay, so that's some of the important thing about this. Another way that we define pressure is this. It's going to start with the force divided by the area. Okay. So if we look at the force, especially if you look at some of the object inside of the fluid, what is the force of the object? So if you're standing just right below this one here, you're going to feel a pressure, right? And the pressure is coming from this block. So if you stand below a block, then you're going to feel the pressure from the block. So what is the pressure that you feel? It's actually the weight of the block. So I can say the mass times the G, which is 9.8, that is the force. That's the force that you feel. Now, if you just stand right below this one, and the area is going to be the area of the object. So I have this object here, and this object has an area A, and it has a certain height, and this is the H. So I can say my area is equal to my volume divided by H, right? Because this rectangular, if you look at the rectangular object, the volume of the rectangular object simply is the area times the height. So volume equal to A times height, and I can say A is equal to volume divided by height, which is this one over here. I can reorganize this one. I'm going to multiply H on top and the bottom, then I will get the mgh over the volume. Now look at the first two things over here, N and V. Isn't that familiar to us that we just define something related to this? And that's this one here. So I can rewrite this equation. So this is also a pressure. I can calculate the pressure if I have something in the fluid and I know how much depth like the depths that I'm inside of the fluid, then I can find out the pressure due to the depths, due to I'm below the surface of some kind of fluid, then I can find out the pressure. Now the density of here, the rho over here is the fluid density. It's not the object density. Okay, so it's not the density of someone below this object. Is no, it's the density of the fluid times the g times the height, and that is also another way to calculate the pressure. Okay, any question about this? Let me see what's the next topic. Okay. So now we are ready to look at one of the important equation that you will do the calculation with the equation of hydrostatic equilibrium. Okay, let's look at that one. This has to do something like this. Okay. Let's say I have a tank of water. Okay, the tank of water. Now this one is water. And outside of this tank, there's an air pressure, right? Air pressure is always there, okay? How much of air pressure is? This one here, 1 atmosphere, 10 to the 5th Pascal, 14.7 psi. So that's the air pressure. Let me denote P0 to be the air pressure. So this is an air pressure. And if I have something not on the top of the water, just below the water, let's say I have an object here. This is the location of my object, and I wanted to know what is the pressure at that point. Would this pressure equal to P0? Would this pressure under the water be the same as the air pressure? Or is it going to be more, or is it going to be less? What do you think? Anyone want to try to guess? No? You think about this then, so if you have something over here, you're going to feel the pressure from the water above you. You're also going to feel the pressure from the air because the air pressure also push downwards. So at here, at the bottom of the water, you're going to have two pressures. One pressure is coming from the outside, which is the air pressure. So the pressure that you're going to have is going to be plus the pressure from the water, and it was because you are underneath of the water and all this weight of the water is going to push on you. And the way we do this calculation is if you know the depths, which is the H, then you can write this as the rho G and H. And this rho over here, if you are using the water, then this will be the rho of the water. If you're using the oil, this will be the density of the oil. If you use salt water, this will be the density of the salt water. So that is the what we call the equilibrium, the hydrostatic equilibrium. Why do we say this is static? That means nothing is moving. You just simply put an object inside and you want to say, I want to find out what is the pressure underneath of the water. Okay, so this could be a very big number. Depends on the depths. I'm not sure that any one of you like diving, and so if you go diving, and especially if you dive in the salt water, like in the ocean, and you need like a very special kind of the suit, because when you are underneath of the salt water or in the ocean, that pressure is quite large, and you have to protect yourself. That suit is actually try to help you to adjust to the change of the pressure. So um, this is how you can find out what the pressure from the seawater. So if you are underneath an ocean, this one here, you're not going to use one. You're going to use the saltwater density, and you multiply it with the G9.8. You multiply it with the depths, then it will give you this the pressure underneath of the salt water. Okay, so that is what we call the equation of hydrostatic equilibrium. Now, the last thing we want to talk about is the gauge pressure. So, just give you the definition what that is. So, gauge pressure is if you know like there's like a pin shape like a tire pressure gauge if you have that kind of things. So the reading that you got from those like a tire gauge pressure is they give you a number which is actually not the pressure inside of the tire. The equation to relate the pressure between the actual pressure and the gauge pressure is this. The reading that you read from the instrument that you use to measure the pressure is actually equal to the actual tire pressure and minus the air pressure. So the actual pressure inside of the tire should be the reading that you read from the instrument plus 1 atm. Okay, plus 1 atm, that is the true pressure that inside of the thing that you try to measure. So that's what we define as the gauge pressure. So what about the blood pressure? So what is the blood pressure? Where do we feel the blood pressure? Where is the blood pressure that we feel from? Well, any kind of pressure, you need a force, right? And where's the force coming from the blood? Well, you know, the heart is beating and the heart actually contracting. And when the heart starts to contract, it's like a pump. It will pump out water, and because, well, not the water, it's going to pump out the blood. That blood, because of the pumping, is going to give you a blood pressure because it's going to give the blood with a force, and you the blood vessel is going to feel the blood force, and if you divide the force with the area of the blood vessel, and then you can find out the blood pressure. Now, the blood pressure, when you wanted to find out that, if you go to a doctor, when they take the measurement of your blood pressure, if you notice, they always going to raise your arm. If they measure the pressure from your arms, they're not going to say, "Oh, just lay down your arm and we're going to measure your blood pressure." They're going to ask you to raise your arm, and when you raise your arm, you're not going to raise all the way up. You're going to raise your arm to be at the same height of your heart, because that's the heart blood pressure. If you are raising your arm to the higher place or lower place, the pressure that you measure is not going to be the true blood pressure. Because when you raise your arm to the top, you are going to have a high difference between your arm and your heart. And that difference is going to apply to this equation over here. that is going to not going to give you the true pressure of your heart. So in order to measure the blood pressure, you're going to make sure that you don't have this effect. You don't want to have a high difference, because if you have a high difference, then the pressure that you measure, the gauge pressure, is not going to be equal to the true pressure. You try to eliminate this kind of effect. So the blood pressure, when you measure that, you have to make sure that your hands is at the same height as the as your heart. Okay, let's see what else I wanted to talk about. Okay, the last thing I want to talk about is how we measure the blood pressure. So um, right now, most of the things that we use to measure the blood pressure is like an automatic, like a machine, right? There's going to be a pump and pump by the electricity. But in the old way, that when we measure the blood pressure, we use this kind of instrument. Um, you probably see that some of the medical professions still like to use this kind of blood pressure instrument, and the devices are very simple. So this is kind of a different way to represent that. You can see a column of the mercury. So inside of that is like a silver things. The silver like shining thing is the mercury. Right now, because mercury has some, it's a poison. So the vapor of the mercury will cause cancer and probably will poison you. So we don't use mercury a lot. But we use mercury because it's the heaviest fluid on Earth. The idea is this. One of the homework problems you're going to see is they're going to describe what this barometer is working. When you wanted to build a barometer, which is an instrument to measure the pressure, you put a tube, and you put the tube submerged into this tank of the fluid, fully submerged. And you want to get away all the air inside the tube. So when you submerge the tube, let's say the tube is here, then inside the tube should be the same mercury outside of the tube as well. Once you submerge, fully submerge it, you get away the air, then you lift this one up. When you lift this one up, what happened is the height of this mercury will start to drop down. And why would this drop down? Well, because when you lift it, it's not horizontal. When you lift it, all this mercury is going to have a mass, and the mass will be attracted by the Earth, and the force of the Earth is going to try to put it downwards. So inside of this mercury, this block of the mercury is going to have a weight. This is the mg, the weight of the mercury. Well, on the other hand, you also have an air pressure. Air pressure is going to push this one, push the surface of this one here. And when it push to this tank of the mercury, it will also push the mercury go outwards inside of the tube. So this one is actually the force due to the pressure. This is the pressure force. So you have two forces coming at the same time. When they are the same, these two forces are the same, and it's going to reach to equilibrium, it will stay at the same height. Okay, why would this one change its height? Well, because the mass depends on the height. If you have a more of the mercury on top of this surface interface, you're going to have a more of the M. So that means the outside pressure is larger, or outside pressure is smaller. This will have less of the mass. So that's the idea. And that's the idea of the barometer. If the outside air pressure is larger, then what happened is the mercury is going to raise higher, and then you will get some number will be larger than 760. 760 is the number when you have a 1 atmosphere pressure, and you 60 millimeter, that's 76 centimeter. Okay. All right. Any question about this part? I don't have much of time, but let me just go through some of the question here. This is one of the question. They show you this one, but I don't think we talked about this already. Let's see. Okay, I'm going to skip this one. We will go back to this one when we talk about the buoyancy. Let's do this. Some of the problem over here. The first example I wanted to show you, this one here, is the density problem. So I already give you one simple one. Now here, you study an unknown metal. So unknown metal meaning we try to find out the density of the metal. So here, this problem is try to find out what is the density of this one here, because each one of the material has a different density. And I tell you the density is a cylinder. So it's like this shape, and this is the object. It has a height. The height is 10 centimeter. And the radius of this one here is 4 centimeter. So this is a R. And we found the mass. We try to find the mass. So we hand this one by a spring, and the spring give us this. The spring give us spring constant. They give us spring constant. So we put this one on, connect this one to a spring. So this one connect to the spring. Spring has a spring constant, and that's the number. Now, when this one put it to a spring, it is stretched, so it will elongate. It's going to have a change of the length. So it's going to increase the length by this much amount. And we want to find out what kind of material is this. So how do we start? How do we deal with this one? How do we solve this problem? Well, the first thing you probably have to do is that you can try to draw a free body diagram of this. Why do we need to draw a free body diagram? Because if we want to find this solution, because we wanted to know the density, we have two things that we need to know. We need to know the mass. We need to know the volume. Well, to know the mass, we can also find out what is the weight, right? If we have a weight, we divide by the G, 9.8, and we got the mass of this one here. What is the volume of this object? Well, this is a cylinder, so the cylinder is going to be the area times the height. If we know the area, right? We are given with the R, so pi R squared is the area, and times the 10 centimeter, that is your height. So you got the bottom part already. What we need is actually, can we get a weight of the object? Which means the weight is when you draw a free body diagram. Let's say this is an object that we try to measure. The object has a mass, so it's going to have a weight. So this is the weight of the object. Now we also, at the same time, it's going to be pulled by the spring. Here we're going to have a spring force. So this is a spring force. How do we calculate spring force? Spring force is based on the Hooke's law. The Hooke's law tells you it's going to be equal to the spring constant times the change of the length. But the change of the length is 0.404 centimeter. You have to do some conversion. So this one is 9517 Newton per meter. And you multiply this one here, 0.404 centimeter, and convert this one to meters. So that's 100 centimeter equal to 1 meter. And then you can get this one to be a Newton. Okay, so once you get this one Newton, and then you say this one is simply equal to F of S. And that's equal to your M times G, right? So you got a mass by this way. So this is how you are going to find this result. Now, once you do this, then you got the mass, then you can find out the density. After that, you look at the table in your textbook, then you will be able to find out what material is this. I'm not going to go through the detailed calculation. I think that you can calculate that. Let me just give you the density of this object. So if you do it correctly, the density of the object is going to be equal to 7.79 times 10 to the third kg and meter cube. Okay, I'll let you do the rest of the calculation by yourself. Question about this problem? Okay, let me go through one more problem over here. Here we are looking at a steel storage drum, a 55-gallon storage drum. And using an air pressure, we wanted to evacuate the air inside of the drum. Gallon is another unit, is a volume unit as well. And they tell you if you have this 1 gallon, which is equal to 4,000 centimeter cube, and you have 55 gallons, so you can find out the total volume, right, by using this one. And it tells you typically this drum is going to have a radius of this much. Air pressure is this much, it's actually 1 atmosphere. So to solve this problem, the first thing you have to know is the drum has a shape like a cylinder, right? This is a cylinder, just like the drum. We're given a lot of information here. We're given was the radius of this one here. So the radius of this one here is 0.310. You also given was the volume. Okay, so the volume, the total volume is 55 gallon. And you can do a conversion because 1 gallon is equal to 4,000 meter cube. So that's how much of a volume of this drum is. If we know the volume and we are given this one here, which is the radius of that, it's actually try to help us to get the height. So what we wanted to know is actually what is the height of this drum. So we can get the height of the drum if we know the surface area of this one here, right? So what is the surface area of the drum? The surface area of the drum is equal to pi r squared, where r is equal to 0.310. So that's the area. And you use the volume divided by the area, that will give you the height. So if you put that into the equation, you're going to get a height about 0.728 meter. So you can verify this by yourself. I'm not going to do the calculation in detail at here, but you can do the calculation. So what do we need height for? Well, because we need to know what is the total area inside of this drum, because the total area is this. The total area of this drum, including the top circle and bottom circle, and also the size. Okay, so this size is like a hoop. So the total area is going to give us the pressure, because your total force from the atmosphere pressure on the drum is the total force divided by the total area is equal to the atmosphere pressure. Okay, so we need to find a total area. So what is the total area? It's equal to 2 times this top and bottom circle area plus the hoop, this hoop, okay, the hoop area. What is the hoop area? You find out what is the circumference of this one times the height, and that will be the area of this hoop, right? So that is going to be 2 pi r, which represent the circumference, and times the h. That will be the total surface area of this part. And this one is the pi r square, and you times 2. That will be the area of the top and bottom. And you sum these together, you're going to get a total area. The total area is equal to 2.02 meter square. And now once you get this total area, and you know this pressure is 10 to the fifth, so then you can find out what is the force inside. What is the force? Well, what is the force? The total force, okay? So total force of this one here is going to be equal to P ATM times your A total. P ATM is 10 to the fifth Newton per meter squared, and area is 2.02 meters squared. So you can get the force coming out from this atmosphere, which is 2.02 times 10 to the fifth Newton. That's how much of the force acting on this drone. So if you want to crush this, you have to provide the other direction of the force, which will be the force that pushes it downwards, right? So what is the inside force? The inside force that push to the outside is the pressure inside, and that you times the total area. Do they tell you the inside pressure? That if you look at here, the inside pressure of this is going to be 0.5 times 10 to the fifth Newton, which will be the force, because you have a force coming in all directions, and that much of the force will be equal to your inside pressure times the area. Because you have two sides, right? One on the top and one at the bottom. So you got the inside force to be half of the pressure times the area. So if you multiply with the area, I should multiply area over here, 0.2. And that will be your force of the inside. That means you got 1.01 times 10 to the fifth Newton. And if you have the inside, which is 1.01 times 10 to the fifth, however, the outside of the drone is 1 atmosphere. So your net force to crush this one has to be equal to the force of the inside minus the force of the outside, because the outside is coming downwards and the inside is going outwards. So this one will give you the force that required to crush this drone. Okay, So this one is 1.01 times 10 to the fifth Newton, where the outside is going to be 2.02 times 10 to the fifth Newton, which means you're going to get a negative 1.01 times 10 to the fifth Newton. What the negative means is you have to go inwards. So in order to crush that, you have to go inwards in this way. Okay, any question about this part so far? Let's finish this one real quick, right? I'm just going to take a little bit more time because the blood pressure is one of the question has a like a bio-related applications. I wanted to use this one to show you how we do the calculation about the blood pressure. Okay, so if you go to a doctor's office and they're going to measure the blood pressure, 95/75 is kind of normal. So what does that mean to us? So first thing that we were trying to do is, can we do some kind of conversion? If we know the atmospheric pressure in millimeter of the mercury, where does this one coming from? If we want to convert this one, let's say 95, how do we convert 95 into like Pascal? We already told you this one is equal to 760 millimeter of the mercury. So this is equal to 1 atmosphere. Okay. So if you say this, there's like a two pressure, right? I'm not a medical expert, but the systolic pressure is the one with 95. So the other one is diastolic pressure. So if you have a 95 millimeter of mercury, and you want to convert into the Pascal, which is equal to Newton per meter squared, how do you do conversion? Well, you multiply with this one here. So I know 760 millimeter of mercury is 1 atm. And I also know like a 1 atm is equal to 10 to the fifth Pascal. So if you do this one, then you can convert this one into Pascal. So this will give you 1.14 times 10 to the fifth Pascal. And similarly, you can do this one if you wanted to do the diastolic blood pressure. Now, the 75 here is actually not the pressure of this one here. The 75 simply tells you the change of the pressure. So if you wanted to find out what is the diastolic pressure, you have to use this hydrostatic pressure equation. The 75 actually is this number over here. It's the change of the pressure. This is a 75. The actual diastolic pressure is equal to the atmosphere pressure, which is 760 plus the change of that. So if you do the calculation, this pressure should be equal to what, like 760 plus 75, that will give you 835 millimeter of mercury. And then you have to, if you wanted to convert into the Pascal, you do the same thing like this one here. You multiply 1 atm and divide by 760, and you multiply 10 to the fifth Pascal over 1 atm. That will give you the result of this one, which will be equal to 1.11 times 10 to the fifth Pascal. Okay, so that is very similar to like a gauge, the gauge pressure that it's not really give you the pressure inside directly. Then you have to actually add with the atmospheric pressure in order to get the final answer of this one here. Okay, I hope this will give you some idea about the basic things about the fluid. We are going to end it here. The next time we meet, we're going to spend some time to discuss the buoyancy. We are also going to talk about the fluid in motion. We will probably introduce the Bernoulli equation, which will give you an idea of what happens if there's a pressure difference. Then you know pressure is going to flow from high to low, and we're going to do some calculation based on that. Any question? Thank you for joining me. I wish we had more people join me as well. If you don't have any question, then I will see you next time. And just to remind you, I will post the correction problem online. I would also post a video about the homework one hint. So if you wanted to take a look of the hint before you do the homework, and I'll be fine, and I probably will help you to answer the question in the homework. All right.
Thank you.
Thank you.
Thank you.
All right, thanks.